Good morning. It's been quite a morning. Not quite sure I would get here on time, but I did, so that's good. All right. All right, guys, let's go ahead and get started. And let's pick up where we left off. We just started looking into chapter 20. And so we said chapter 20 was all about carbonyl compounds, right? So we're going to start seeing a lot of the carbonyl chemistry. Acid derivatives, aldehydes, ketones, and like I sort of alluded to, we're going to start off with sort of the context of oxidation reduction. We've seen, we had a whole chapter dedicated to oxidation reduction. You're going to see there's a lot of different contexts in which redox reactions can take place. This is going to be one of them. All right. One broad.
There. Bless you.
One broad category of reductions of carbonyls is called hydride reductions. And you can probably guess what type of species we're going to use here, right? Go ahead and say it. Hydride. Did you say hydrogen? It's hard to tell with the mask on. I'm just going to assume you said hydride. Yeah, hydride. And what is hydride? What's a hydride ion look like? You guys know this. Be annoying and make you tell me. Hydride. Like a battle of wills here. Everybody's staring at me. What is hydride? I'll make you guys be interactive. Google it if you don't remember. H minus, there you go. Yeah, hydride, H minus. All right, so basically what we're doing here is we are using sources of H minus, and then we're going to do that. Then we're going to use those in one of those particular nucleophilic additions or nucleophilic substitutions that we talked about the other day. All right. Well, first of all, let's make a list. Let's make a list of hydride sources. These are going to be, there's lots of them. These are going to be some of the more common ones, though, that we are going to run into. All right. There's three broad bullets here I'm going to put. The first one includes two of them. All right, you have two agents here. One of them is called lithium aluminum hydride, and that has the formula LiAlH4. We've seen this before, actually, in a previous chapter. And also NaBH4. It's called sodium borohydride. They're both very, very similar. They do a lot of the same things, although the lithium compound's a little bit more versatile. You can do a little bit more with lithium than you can with sodium, but they both basically serve the same function. All right, the second one, and I can never remember the name of this one, so I'm going to look. Diisobutyl aluminum hydride. The reason I don't remember that is because I always go by the acronym. Di-val-H. Di-val stands for diisobutyl aluminum, and then the H just represents the hydride that can be plucked off of it. And then there's another one. Now this one sucks because this one has a really long name and no acronym. Lithium tri-tert-butyl. No, butoxy, sorry. Aluminum hydride. Can't believe the nerve of the people who wrote this book to put this in there, put this obnoxious name and not give it an acronym. What should we call it? I'm going to give it an acronym. Not exactly catchy, but I'll call it LTTBA. That's almost as bad as the real name, though. Doesn't have a good flow. But anyway, this is a legitimate reducing agent for hydride reductions. All right. Now, one thing about these is certain ones of these are used in certain situations. Sometimes they're effective, sometimes they're not, depending on what they're mixed with. All right. One thing to remember about these two up here, lithium aluminum hydride and sodium borohydride. Those are strong reducing agents. They're strong hydride sources. Whereas the other two, di-val-H and LTTBAH, those are mild hydride sources, mild reducing agents. It's kind of like going back when we did oxidations of alcohols, right? Y'all remember, we said PCC was a mild oxidizing agent. Something like potassium dichromate was a really strong one. Kind of the same thing. Yep. So these are going to be the primary hydride sources that we're going to be working with. Now let's see how we can use them. All right, first, let's see what happens with aldehydes. So let's say we have an aldehyde. And let's say we have a strong hydride source. I'm going to draw it like that, just for ease of mechanism drawing. All right, well, think back to the other day. What types of reactions do aldehydes go undergo? Remember, we had two broad categories. Which one was aldehydes in? Group one, which was nucleophilic addition. All right, so this should undergo nucleophilic addition. Keep that in mind, okay? All right, suggest to me in mechanistic step, what do you think is going to happen? Go by the general nucleophilic addition guidelines if you need a little bit of help. Is there a good target for attack? I think that's going to happen. Something's going to happen first, though. What would cause those pi electrons to move up? Let's think about the reducing agent, right? Lithium and aluminum hydride. What did we say its purpose was? To serve as, what's that? A strong hydride source. So what do you think it's giving off? H minus, hydride, right? So you have H minus. What do you think H minus can be attracted to? A partial positive on carbonyl carbon. Boom. Yeah. Get used to seeing this arrow going to a carbonyl carbon. That's going to happen a lot over the next 3 chapters. Carbonyl carbons are really, really good site for nucleophilic attack, right? And H minus is a strong nucleophile. So yeah, it works. And gray, as you said, that will cause a pair of pi electrons to move up on your oxygen, right? This carbon had 1 hydrogen before, now it's got 2, just for skeletal structure purposes. I won't draw them, but they're there. All right. Now, when we did nucleophilic addition the other day, the general one, what did we typically say happened now? This is actually a 2-step reaction. The first step was adding lithium aluminum hydride. What do you think the second one is? Add water, add a proton source, right? Water, methanol, ethanol, something like that. That's going to serve as a proton source, and it will protonate that negative oxygen. And boom, there you go. You have an alcohol. Not just any alcohol, primary alcohol. Whenever you do a strong hydride reduction of an aldehyde, you always get a primary alcohol. That's a very dependable trend that you can see. Okay. Yeah, that was a small aldehyde. We could put a bigger one in there, right? We could even like attach a benzene ring or something. We'll use sodium borohydride here just for funsies and methanol. Right? But it still works exactly the same. H minus attacks your carbonyl carbon. Which then, and then you see a protonation of your negative O, again to make a primary alcohol. Very reliable, very reproducible, does the same thing over and over again. Always get a primary alcohol. That's the nice thing about hydride reductions. They're very much predictable, more so than some of the other ones we're going to see. Okay. So far, so good. Any questions on how we got that? All right, let's see what happens with ketones. All right, the only difference between a ketone and an aldehyde is that a ketone has 2 R groups attached to your carbonyl carbon instead of just 1, right? And there's no H directly attached. Otherwise, it's exactly the same, right? You're still going to have an H minus. You're still going to have that same partial positive there that gets attacked. You're going to get a negative O. Then you're going to have a proton source that comes in and protonates it. Yeah, mechanism is exactly the same, no differences whatsoever. However, what you end up with is a little bit different, right? What did we get here? You get a secondary alcohol. Yeah. Whenever you do a hydride reduction of a ketone, you always get a secondary alcohol. Always. Does that make sense? Yeah. Stands to reason. Now, there's something else here that we didn't run into with reduction of aldehydes. Can you guys spot it? This particular one, we had a situation that we did not run into with aldehyde reduction. Take a look at your product. Who said that? I don't know where that came from. Kristen, what'd you say? Yeah, guess what? We made a stereogenic center. Ooh. When you do a hydride reduction of an aldehyde, it is not possible to make a stereogenic center. Right? No matter what, by definition, you're always going to have two H's. The only exception would be if you had like an isotope like deuterium or something, which is not something you're going to run into very often. But here it is possible. You're not always going to have one, right? If this had been an ethyl group, for instance, then this wouldn't be stereogenic. But if those two R groups are different, then yeah, it's definitely possible to have a stereogenic center. So we got to figure out, okay, are we just going to get a front side attack? Are we going to get back side attack or both? Do we get one stereoisomer or two or what? Well, again, the answer always lies in the step of the mechanism where you saw attack on that carbon. And that was the very first step. You've got to figure out where H minus could have come from. Would it have favored one side over the other, or is it equal chance it would come from both sides? What do y'all think? Who says only front side? Who says only back side? Who says both? Ooh, we have an overwhelming majority for both. Why both? Seems like the right thing to do. See, yep. Well, you're right. It is both sides, right? Again, always look at the hybridization of what's being attacked, right? What's the hybridization of this carbon? SP, SP2, or SP3? SP2, which corresponds to what geometry? Trigonoplanar. Flat as a sheet of paper, can be attacked equally well from both sides. So, that means you actually get a racemic mix of these stereoisomers. Again, you won't always get a racemate. If those two R groups are the same, then you don't have to worry about it. But if you do create a new stereogenic center, it is possible. Or if you do create a new stereogenic center, it is definite that you will need to account for each stereoisomer. Okay. Any questions so far? All right. So we've seen what aldehydes and ketones do with strong reducing agents, strong hydride sources. Let's see what they do with weak. They do absolutely nothing. Yeah. Aldehydes and ketones are not as reactive as acids and acid derivatives. They're only able to react with the strong hydride sources. So if you tried to use like divalh H or something with an aldehyde, nothing's going to happen. So yeah, that's it for aldehydes and ketones at the moment. Anyway. All right. So let's shift gears and then look at acid derivatives. Now, acids and acid derivatives, we said there's lots of them, right? There's carboxylic acids themselves, there's amides, there's esters, there's acid chlorides. These don't all have the same level of reactivity. In fact, let's go ahead and sort of rank these in terms of general reactivity. See, we have carboxylic acids. What else did I say? So we have esters. So we have amides. And acid chlorides. That's it. Let's rank these on a scale where 1 is most reactive, 4 is least reactive. All right. How do we determine which one's most reactive? The more reactive it is, the better a leaving group it's going to have, right? Remember, what type of reactions do acid and acid derivatives undergo? We said it wasn't nucleophilic addition like aldehydes and ketones, right? What was it? What's that, Greg?
You said substitution.
Oh, sorry. By the way, my hearing's not that great anyway, and also with the mask, this makes it harder. So if I accidentally ignore you, it's not because I'm trying to snub you, it's because I literally didn't hear you. Yeah, nucleophilic substitution. In a substitution, you have a leaving group, right? The better the leaving group, the better the substitution can get. Right? Now, what makes a good leaving group? Think about the basicity. This is something we talked about way back last semester. Is a good leaving group going to have high basicity or low basicity? Ooh, that's a long time ago. It's the opposite of what makes a good nucleophile. What made a good nucleophile? A strong base or a weak base? OH minus is a good nucleophile. What's OH minus? A strong base or weak base? Strong base, right? Yeah, strong bases generally make good nucleophiles. So it stands to reason what type of bases are best for leaving groups. Weak ones, yeah, weak bases are best leaving groups. All right. Armed with that knowledge, look at this. Can you tell me which one's going to have the best leaving group? So what are you looking at? You're basically looking at OH minus versus OR minus versus like NH2 minus versus like Cl minus. Yeah, Cl's very, very weakly basic. So acid chlorides are super reactive. In fact, they're hard to control sometimes. If I were to, and I might do this, not today, but in another class, if I were to bring a jar of an acid chloride in here, it's kind of cool. It's kind of cool and kind of dangerous too. You can take the lid off, and it's so reactive, it'll react with the water in the air, and you'll see smoke start forming around the edges. That smoke is actually HCl gas. And then you bring it up, and you breathe it in your lungs, and it really, really stings. you're breathing hydrochloric acid, right? So not a good time. But yeah, it shows you just how reactive acid chlorides are, right? So that's definitely the best one, the one with the best leaving group. Usually, then you have esters and acids, although they're pretty similar. I'm tentatively putting esters at number 2, although there are situations where you could see those reversed. And then amides have terrible leaving groups. Something like NH2 minus. We've seen NH2 minus before. It's a really, really strong base, right? So that means it's a really bad leaving group. So what's the point of all this? This big array of reactivities means that you're going to get different results with different reducing agents. And even when you get similar results, they may happen via different mechanisms. All right, so we're going to take it sort of category by category here. The first category is going to be acid chlorides and esters, because actually in this context they do the same thing. All right, so let's see what happens here. Let's use an acid chloride. All right, let's put in a strong reducing agent. All right, so let's use lithium aluminum hydride. All right, what do you think is going to happen here? Give me a mechanism step. H isn't going to attack the Cl. Remember, Cl is very electronegative, so it's got a partial negative. Those two would repel each other. What's that? I'm sorry, Marissa, I couldn't hear you. Yeah, just like we saw previously. We're going to get attack at the carbonyl carbon. Yep. Partial positive. Great spot for an H minus to attack. All right. What's going to happen in turn? Well, that would give that carbon 5 bonds, which is a big no-no, right? So something's got to happen. Double bond move up. That's actually not going to happen in this case. That's what would happen if we had a nucleophilic addition. This is going to be a substitution, so something else actually is going to happen. Cl minus is going to leave. Right. It's going to get booted off. And what does that make? Makes an aldehyde, right? Very good. Any questions about how we did that? Guess what? We're not done. Tricky, tricky. Why aren't we done here? This looks, great. We got a nice stable aldehyde, looks like. Why aren't we done? Has nothing to do with the Cl. Cl is just a byproduct. It's off to the side. Think about your product here. You have an aldehyde. You have an aldehyde in a system that contains H minus. What do we know about aldehydes and H minus? They react, right? So yeah, what can happen here is another molecule of LiAlH4 can come in, give off an H minus, and then you get a subsequent nucleophilic addition. So yeah, you got to watch out for these. These will get you. These are tricky. So these also produce primary alcohols. Reason being, the intermediate product aldehydes are still reactive towards hydro. Excuse me. Yes, sir.
So what if you did this reaction with like a week?
Oh, excellent question. I am going to get to that in just a minute. Right? Y'all see why we got that? Now, strictly speaking, if you're writing your reaction scheme over here, really, you should put in 2 equivalents of that. For some reason, it's become acceptable in general convention just to put this and assume that you have 2 equivalents of it. So if you just see this and don't see the 2x, it's still going to do this. I think you should write the 2x, but again, that's just my personal opinion. Okay? Same thing would happen for an ester. All right, the only difference is you have a different leaving group. When you do it with an ester, oops, not there. Exact same thing happens. The only difference is your leaving group is OR minus instead. Okay. Any questions? How we got that? All right. Now, Josh had a good question. What happens if you use a weak reducing agent? Let's do that. So in that case, you typically see something like this. You use dival H with follow-up of 1. Right? Mechanism-wise, everything runs as you would expect, right? What's dival H going to do? It's going to give up a hydride, and as we've seen, hydride likes to attack carbonyl carbons. When it does so, leaving group can leave. And that gives you an aldehyde. This is where things change though. We saw previously that aldehydes don't do anything with the weaker reducing agents. That still holds true here. So if you want to convert an acid chloride or an ester to an aldehyde, this is how you do it. That's your final product. All right. We could do the same thing with the exact same thing with the other mild reducer. I'll be brutally honest. Whenever I'm doing these, I much prefer writing dival H to that other one, just because it doesn't have a catchy name. But just know it does the same exact thing. All right? Yes, ma'am.
So even with like the NH2 as the leaving group, is it still gonna do that? Just be harder for
Nope.
the system, or?
Yeah, I know, Marissa. Wouldn't it be nice if that was the case? But unfortunately, it's not. They do different things. We're going to see that in just a minute. Any questions about how we've gotten this far? All right, let's take a look at carboxylic acids. All right. So let's put a carboxylic acid up here. All right, let's see what it does with lithium aluminum hydride. Well, honestly, we don't really see a whole lot of difference here. H minus is still given off by your reducing agent. It's still going to be attracted to your carbonyl carbon. The only difference is, again, the leaving group. What's the leaving group going to be? OH minus, yeah. That produces negative oxygen. Oops, oh, wait a minute, nope, sorry, getting ahead of myself. That produces an aldehyde. And what did we see last time? What can aldehyde do? Yeah, it can further react, right? So this is exactly the same as what we've seen before. All right, we produce a primary alcohol. So carboxylic acids plus strong lithium aluminum, I can never say that. Lithium aluminum hydride, it's a tongue twister. That produces a reduction all the way to the alcohol, primary alcohol. Okay? So far so good? All right, let's see what it does with weaker producers. So let's put it with something like dimethyl H. This case, no reaction. So that's where it differs from acid chlorides and esters. Acid chlorides and esters can react with this to make an aldehyde, but acids just not reactive enough. So the only thing acids react with in this context is going to be lithium aluminum hydride. Okay? Does that make sense? Questions? All right, we're rolling right along here. Then we get to amides. And you're going to love this. My collective wrong. All right. Now, you can have three different types of amides: primary, secondary, and tertiary. All right. What I'm about to show you works for both primary and secondary amides. I'm going to use a primary amide as an example. Okay. Now, this one's a little bit different. All right. I told you that out of all these, amides had the worst leaving groups. So like in this case, if H minus were to attack here, it would try to kick off an NH2 minus. NH2 minus is extremely basic. In fact, it's comparable in its basicity to H minus itself. So guess what? That don't happen. However, the reaction does proceed. It just does so in a different way. I'll draw it like that. Here's what happens. This is going to be very different. Basically, what's going to happen here is H minus is not going to act as a nucleophile. It's going to act as a base instead. All right, what do bases like to do? According to the Bronsted definition. They like to accept protons, yeah. And what it's going to do here, it's going to pluck a proton off from your nitrogen. And that's going to cause a bit of a domino effect. These electrons are then going to jump down in a carbon-nitrogen double bond. And those electrons are going to move up to oxygen. So you're going to get that. Then let me back up a little bit here. Whenever you have lithium aluminum hydride, remember that's a salt. It actually dissociates into Li plus and AlH4 minus before it gives off its hydride. Right? It's just like table salt or any other ionic compound, NaCl. Right? So this dissociates. The AlH4 gives off an H minus, and you actually have this left over. This oxygen can then bond to that aluminum. Give you that. Okay, y'all with me so far?
Where did the seal come?
It came out of the imagination in my head for some reason. I don't know why. Thank you for asking about that. That should be an H, not Cl. Guess I still had Friedel-Crafts reactions on the brain, eh? All right. Okay, now, at this point, another lithium aluminum hydride can come in and it can give off an H minus. So that's 2. All right, here's the H minus from that. It's going to attack here, and this is going to leave. And actually, if you used exactly 2 equivalents, you could actually stop right here. This is actually a stable compound. It produces this. This, by the way, is called an imine, not amine, imine, also known as a Schiff space. But it has a carbon-nitrogen double bond. All right, so that's actually a stable molecule. However, usually what happens here is that this is provided in excess. So that means you have an abundance of it. Once you make your imine, guess what? A third lithium aluminum hydride can come in and give off an H minus. That third H minus can attack right there on the carbon of the double bond. And it can cause a pair of electrons to move over to nitrogen. And that means nitrogen is going to have a negative charge. Wouldn't it be nice if we could satisfy that negative charge with something? Do you think we can? Yes. What do you think we can satisfy it with? That we haven't drawn yet. I think I heard somebody whisper H2O. I'm not sure. I'm going to assume I did. Yeah, add in a proton source like water or methanol or something. And boom, you get your final product. So definitely a bit different than the other examples we've done, but still, it is definitely a reduction as well. We've gotten rid of these 2 carbon-oxygen bonds. Okay? So this is an amine. I don't know how much we've talked about amines, but it is one. Amine. What type of amine? So primary amine, yeah. Can I erase? Let me write you some guidelines here. All right, if you start off with a primary amide, you do a hydride reduction, you get a primary amine. Start off with secondary amide. Think real hard. What do you think you get? Secondary amine, yeah. Use a tertiary amide. Think real hard. What do we get? What's that? What'd you say, Marissa? No, say that out loud.
I said I feel like this is a trap.
You feel like this is a trap? What the heck, man? Do you guys not trust me? I love how easily you said that. Oh, no, not at all. Well, here's the thing. You can't trust me.
I knew it.
What you gotta do is trust yourself. Trust your own sense of logic and reasoning. Don't try to read me for context, please. I know, I used to be a student. I know, if he said this in this manner with this tone, that means it's going to be the opposite, and it's going to be this, and I'm going to tie my head up in knots. No. Well, yeah, sometimes, but sometimes not. Trust yourself. What do you think happens if you try to do a hydride reduction with a tertiary amide? What's that?
No reaction.
You are absolutely correct. But now you know what I'm going to ask. Why? Why not? I even prefaced this by saying this only works with primary and secondary amides. That's enough context right there to tell you no reaction. But from a chemistry standpoint, why not? At a molecular level. Why can this not work? And let me draw a tertiary amide. Here's an example of a tertiary amide. Why would that not work? What's that? You don't need two H's, but you do need at least one. This nitrogen has got to have at least one H, because guess what the first step of the mechanism is? You pluck off an H from this nitrogen. If there's not one there, then it gets roadblocked. So yeah, that's why we don't get any reactions here. Yeah? Does that make sense? All right, so that's amides and strong reducers. Before I get started with this, and in my most monotone, flat poker face / voice possible, what do you think will happen when we use an amide and a weak reducing agent? Nothing? You're right. Any amide, whether it's primary, secondary, or tertiary, try to use a weak reducer, no reaction. All right, very good. Any questions about hydride reductions? I'm impressed. We finished that whole section. Woo! That's a pretty good stopping point, because the next thing we're going to get into is organometallics. That shares a lot of similarities with hydride reduction, but has its own features as well. So we will do that on Wednesday. I want to say no quiz this Wednesday, because I want the extra time to teach. So, all right. Yes, sir. I'm still working on lab. I will send something out about lab today. I still haven't decided yet.
Because we get to class today, Wednesday, or Thursday, Friday, and Monday out.